Okay, can you all hear me? Good morning to all of you. Can you hear me? Testing, testing. Hello, testing, testing.
Morning.
Oh, can you hear me? Okay, very good, very good. I thought my mic wasn't working, Okay, all right, please scan this QR code to take this morning's attendance for the admin department's record. Okay, please scan. Please do not draw anything on the screen. It will disrupt the lesson. Whoever has drawn something on the screen, please remove it. Okay, all right, let's resume our lesson. I'll just recap the last few slides of yesterday. I think up to, somewhere, matrices, sigma done already. Okay, so last few slides. So yesterday morning, we're talking about sigma notation. So the sigma means summation. Okay, everything is plus. All the terms are plus, 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 no minus, because it's a summation. And this summation, sigma, is commonly used in statistics. It is also used in your engineering mathematics and in other mechanics engineering modules. But it's very commonly used in statistics, basically to sum all the 1,000 terms or 2,000 terms, okay, collapse into just one term, using the summation. Okay, right. Oops. Okay, and I've gone through a few examples on how to expand the summation term. So likewise, you can also sum all these terms. You can also go the other way. If you have many terms on the right, as you can see here on this screen, you can use the term on the left to sum all these terms together. So all these 1,000 terms or 2,000 terms on the right collapse into just one term. Okay, and it becomes very precise. So when a summation has, for example, k is equal to 1 to k equal to 4, that means you have only 4 terms. So your first term on the right will be when k is equal to 1. The second term on the right will be when k is equal to 2. The third term on the right will be when k is equal to 3, and the fourth term when k is equal to 4. And just leave it as it is if you're asked to expand, okay? All right. Whereas you have if k goes from 0 to 4, then you have 5 terms on the right. Okay. Then we went to complex numbers. Now, we know that numbers like 2, 5, half, 6.5, these are all real numbers. But when you encounter a square root of -1, which in some modules, like in control theory modules, you frequently come across square root of -1, okay? And the symbol used is either J or I. Okay? Different people will use different symbols as long as they define what that symbol is, which is okay. So J is equal to square root of -1. So therefore, J squared is equal to -1, okay? And of course, J is square root of -1. It's a imaginary number because it's not a real. If it's not a real number, then it is an imaginary number used commonly in control modules. And I've given you an example solving this quadratic equation. It is called quadratic because quadratic is the power of 2. And you cannot factorize this. Using any factorization method, you will not be able to factorize this. Whether butterfly method, bow tie method, or any method, you will not be able to factorize this. So we then solve it using the formula for equations that cannot be factorized. And we then solve it using a certain formula, and therefore we were able to find out the answer for x. Okay, so the x, and we realize that it's a complex number. It consists of a real and a imaginary number. And this concept is important in control because depending on the answer for X, it will determine whether a certain system, for example, a spring mass system, whether when it's oscillating, whether it is over-damped, under-damped, or critically damped. And I do not want to go beyond this because it can be, this is a bridging course. Okay, I don't want to go beyond what is supposed to be in the syllabus. Then next, we went on to talk about how to evaluate complex numbers when they are added. So normally, Z, just now I use X because the equation contains X. But complex number normally is represented by the symbol or the letter Z. So, for that quadratic equation, this is our answer. It has got a real part, which is minus a quarter, and an imaginary part, which is square root 7/4. Right? So complex number, just like you can actually, if you have a complex number, for example, Z1, Z1 is equal to A1 plus B1J, and another complex number Z2, given as A2 plus B2J. So A1 is a real part of the complex number. B1 is the imaginary part because it has got a J there. Similarly for A2 and B2. So now if the two complex numbers, if they are added together, so how do you evaluate them? You just simply add all the real parts together. So A1 plus A2. And you add all the imaginary parts together, B1 plus B2. So likewise, if you minus one complex number from another, you minus the real part from one another and minus the imaginary part from one another. And likewise, if you multiply two complex numbers together, you just simply expand them. Just like what you do to expand when two equations are multiplied together. When two okay, so when you expand as usual. Sure. Okay, your A1, A2 plus A1, B2J, and so on and so forth. And then you end up with a J here. Okay, you end up with a J, right? And you have a J squared here. So notice that J squared is actually converted to -1. All right, so you will not have a J squared in your final answer. You end up with a J only. So, so therefore, you end up with this bracket, which is the real part, and the next bracket, which is the imaginary part. Okay, so normal addition, normal subtraction, normal multiplication as usual. And then I've asked you to do as homework to do this. Okay, if Z1 is 13 plus 5J and Z2 is 8 minus 2J, find A at Z1 and Z2 and B minus Z1 from Z2. So it's Z2 minus Z1. And also, number 2, find Z1 and Z2. If Z1 is given by this first expression here, and Z2 is represented by the second expression. How many of you have done it? As your homework. None. One way. Let me see how many have done it. Okay. All right. Quite a number have done it. All right, which is good. Yeah. So these are quite straightforward. There's no need for me to go through. You want me to go through A1 and 2? Okay. The problem is that, you see, when I ask you to do as homework and then the following day, if I do it, then you all realize, hey, next time when Prof say homework, no need to do, because in the next session, he will do it for us anyway. So why do it? So I hope you'll be honest to yourself, and then when I ask you to do homework, you really attempt to do it. Okay, rather than relying on me during the next lesson to do it for you. Then the mind become lazy really, which is against the objective of the bridging course. The bridging course is to regenerate your brain, to make it become alive again, remove all the rust, to activate your brain, reactivate back to school, you see. All right, Some say, sir, only for bridging course, can go through, please. Okay, I'll go through. All right. So to go through, I need to go to the visualizer. The visualizer is on my left, so I need to turn to the left for my visualizer. Okay. Okay, right. Okay, all right. Can see, Okay, go like that. First one, okay. So you have Z1 is equals, okay, let me write there. Z1 is equals to 13 plus 5J, okay. Z2, which is a complex number, is equals to 8 minus 2J, all right. So A at Z1 and Z2. So in this case, what do we do? It's simply, what is Z1? 13 plus 5J. What is Z2? 8 minus 2J, okay? So then you evaluate further the real parts together. 13 plus 8. So 13 plus 8 is 13 plus 8, okay? Plus, you can put a J here. You can put a J outside. 5 minus 2, okay? There you are. So it's 21 plus 3J. And that's your answer. Okay? 21 plus 3J. Oops, something blocking your view. Okay. Okay, straightforward. Then B, subtraction. Z2 minus Z1. Okay, so we have 8 minus 2J. 8 minus 2J, that's your Z2 minus Z1. Z1 is 13 plus 5J. Okay, so you put all the the real parts together. That will be 8 minus 13, then minus, you put all the imaginary parts together. So we have minus 2, okay? Then you have a minus 5J, minus 5J. Normal steps lah, as you would evaluate terms like this. So you have minus 5, minus 2 minus 5 is minus 7. Minus 7 is or minus plus 7, so it's minus 7. So it's minus 7J. Okay, minus 5 minus 7J. Okay, that's number 1, A and B. Right. Okay, so that is done. Number 2, the product. Z1 and Z2. Z1 and Z2 is called product. Z1 times Z2 is called the product of Z1 and Z2. Okay, product.
Chua,
Yeah.
I want to ask something. Can you show us the first one that you did? The Z1 minus Z2.
Okay.
That one, the Z1 is 13 plus 5J, right?
Okay, wait a minute. My skin in front, the screen in front is all black. I don't know.
Never mind, you can just look at your one, then you just let me know.
Okay,
Like the Z1 minus Z2, right?
But, I don't know why I can't even see my own screen also. Okay. Okay.
Right. How come is 13 minus 5J? I thought Z1 is 13 plus 5J. So even if I substitute Z1 minus Z2, right, shouldn't Z1 remain consistent as 13 plus 5J?
Z1 is 13 plus 5J. Z2
Correct.
is 8 minus 2J. Yeah.
Yeah.
So then
when you do the Z1 minus Z2, shouldn't it be 13 plus 5J minus 8?
Oh, sorry.
Right.
Yeah, okay. Z2. Okay. Is
right.
Z2, right?
So it should be 5, right? Like positive 5, because it will be 13 minus 8, right?
Z2 is 8 minus 2J. Z1 is 13 plus 5J.
Correct.
So
when you expand it, right?
Mm.
When you expand it, shouldn't it be 13 minus 8 to get 5, positive 5?
The teacher, your screen is not showing.
Your teacher, your screen. Sorry, your screen not showing your visualizer.
That's why I saw the bit of problem.
Yeah, if you can show the visualizer, then you show us. Cause I
wait. I have some problem with my just not something block it. Something just block it, you know. Wait. Very strange. Wait. Seems I'm that's why I say something just block it just now. Can we share again? Once. Second camera. Okay. Can you see now? Can you see?
Yes, a little
Okay.
bit blur though. If you can focus the
Oh.
visualizer.
My strange.
Okay, so be it lah. Never mind. It's okay.
Is
Okay,
it
it's better
better?
now. Okay, yep.
Okay.
So
Okay.
yeah, so because
So 8 minus 13. Because 13 is the real part. 8 is the real part. So we bring them together. So it's 8 minus 13. 8 minus 13. Okay. Then you put all the imaginary part
okay.
together.
No, I get
Minus
it.
2 is
I get it now.
imaginary. Plus
get it now.
5. But this is plus 5, but outside is minus. So it becomes minus 5. So
Okay,
you put
correct.
all the real part together, all the imaginary part together.
Understand.
According to the
I
science.
did it wrong lah. Yeah, I did it wrong. I did Z1 minus Z2. Okay, answer.
Is
Okay, thank you.
Z2 minus
Yeah.
Z1?
Okay,
Okay.
thank you.
Okay, good. If any questions, just unmute and ask. Okay, then you'll get the answer. Just put it on the chat box, but it'll take a while before I refer to it. Okay, so it's 2 is find Z1 and Z2. Okay, so you then put them together. Okay, Z1 is in the question 2. Okay, question 2. Okay, just this is a different Z1 and different Z2. Okay, different Z1 is different. Z1 is 5 minus 2j. So it's 5 minus 2j, real part, imaginary part. Okay, and the Z2 is 2 plus 4j. 2 plus 4j. Okay, so that's your new your new Z1, your new Z2. Okay, multiple. So you just expand as you would do normally. So 5 times 2 will give you 10. Okay, 5 times, then 5 going to 4j will be 20j as plus 20j. Next, minus 2j times 2. Minus 2j times 2 give you minus 4j. And next, minus 2j times 4j will be minus 8j squared. Okay, you got a j squared. And we know that j squared is equal to minus 1. Next, you just put all the real parts together. So 8j squared becomes a real. Becomes plus 8 because this is minus 1. So this is plus 8, this 10 becomes real. Okay, so 10, so 10 plus 20j minus 4j will give you 16j, then plus 8. Okay, so you have plus 16j. That's the answer. Okay. Okay. Some problem again. It keeps popping out. This, don't know why. Let me just problematic. Okay, back again. Okay, any question? No question. Okay, yeah. Go ahead. Yeah.
How do you do the expansion? Shouldn't it be plus 7 instead of minus 7j?
Sorry, say again.
For part B.
For part B, yeah.
For the expansion part.
Here. Yeah.
Should it be positive 7 instead of negative 7?
Positive 7. Okay, this minus 7j. This minus 7j comes from here. Minus 2 minus 5 is minus 2 minus 5 minus. Wait, let me just say 8 minus 13 minus 2 minus 5. Okay. Let me just check. 8 minus 2j plus, this is minus, minus 13 plus 5j. So minus 2 minus 5j. Wait, there's something here. Okay, minus 2j. Surely minus 2. Sorry. The guy go did this part is not correct. Minus 2 minus 5 is minus 7. So minus 2 minus 5 is minus 7. That's correct. So this is
Is it outside the
so
bracket?
minus
It will
2
be plus.
minus 7. So it's so what you can say, this whole thing is 7 minus 2 minus 5 so minus 7. You can say it's 7 if you like. It's
I think
minus
for
2j minus 5j
addition,
is minus 7j. Okay.
for addition, subtraction, I think don't need put the bracket. It's confusing because it's not multiplication. You don't put the bracket.
Yeah,
then,
yeah.
Then you
yeah.
won't be confused.
No. We have to be careful considering the brackets. Okay, let's say as you have suggested, don't put the bracket. You don't put the bracket, you have what? 8 minus 2j minus 13 plus 5, I mean.
Shouldn't it be minus 5j?
Then if you don't put the bracket, then you have a different answer. Okay, so we put a bracket just to make sure that, we do it correctly. Okay,
Wait,
so I know.
Set
So
plus.
yes, so you have minus 2j minus 13, then of course you remove bracket, I mean this will be a minus lah. Okay, so the same thing the same thing. Minus 2j minus 5j, or you can say minus 2j minus 5j, so it's 7. Yeah. Okay, it was my oversight.
Professor,
Yeah.
the second line, why is there a minus between the two brackets? Shouldn't it be a plus?
Z2 minus Z1. Okay, because this is Z2. Okay, Z2, 8 minus this is
No, I mean
Z2.
after you expand in the second line, right? Shouldn't it be a plus?
8 minus 13. 8 minus 13, right? You bring together and
Shouldn't that one be
minus be a
plus?
plus?
it's the same
Oh,
thing.
yeah,
It's the
because
same
like
thing, It's the same thing.
plus,
So I put minus minus 2. Okay, you can put there minus 7j, like minus 2j minus 5j. You minus 7j. You can forget about this bracket. Okay. Whatever you do, it's basically simple addition and subtraction. So you want to put a plus here. You want to put a plus here. You can, but same thing. You want to put a plus here, then you got to put minus 2 it's the same thing. See, 8 minus 13. Yeah. Okay. Minus 2 minus 5. Minus 2 minus 5. Okay,
Wait, but if previously when you put the bracket, right? Then inside the bracket is minus 2 minus 5. Then should the outside one be plus if we are sticking to the bracket format?
Okay.
Because previously you say you have to keep the bracket.
Yeah. It's up to you actually. If you want to keep the bracket, you can. If you don't want, also okay. Okay, let's say you want to remove. You want to remove the bracket. You can do that. You can do that. You can just remove. Okay. Yeah, remove. And then you put a plus and a minus. Plus and then a minus. Okay, minus 2 minus 5. Okay. Then you put a plus there. So basically, if you can do it, if you think that it's less confusing, you want to remove the bracket, then by all means, 8 minus 2j, right? Then you have plus whatever like you have put down. So minus 2, then this will be a minus, you see. So it is a plus, This is a plus, then it will be a minus. So minus 2j minus 5j, you give minus 7j. Okay. I mean, there are various ways how we want to do it. How you want to do it. Okay. All right.
Professor, hi, sorry. For number 2, right? Can you just explain the second line again? Where 10 plus 20j minus 4j minus 8j square. How does the 8j square transfer over to just a regular number?
8j square. J square is equals to minus 1 in the earlier slides. Okay? Because j is equals to square root of minus 1, right? So j square is equals to minus 1. So this is minus 1. This is minus 1. So here, minus 8 times minus 1 will give you plus 8.
Okay, understood. I see it now.
Okay.
Thank you. Sorry.
All right. Okay. Let me use a fresh bit for the next one. Conjugate. Conjugate. Okay. The example on conjugate. Okay. Z1 is equals to 3 plus 2j. Z2 is equals to 4 minus 3j. Okay. So find Z1 over Z2. Okay. So Z1 over Z2 will evaluate. So, okay, so we write down what is Z1. Z1 is 3 plus 2j. Z2 is 4 minus 3j. Okay. Now, so you have a j in the denominator and j in the numerator. So how do we therefore proceed? Because complex number is a plus bj. Okay, z equals a plus bj of this form. You don't have a j in the denominator. So whatever we do, we must convert this into this form. Okay, no denominator for j. You cannot have a j in the denominator, basically. So how to get out this j in the denominator? So the way to do it is, let's write it down first. 3 plus 2j. Okay. And we have 4 minus 3j. Yeah? Just write it down. Z1 over Z2. No change. Now, what we're going to do is we're going to multiply the numerator and the denominator by the complex conjugate of the denominator. Complex conjugate of the denominator. That means the complex conjugate of the denominator is 4 plus. So changing the sign only. Okay. So 4 plus 3j is the complex conjugate of 4 minus 3j. With a sign change. Now you multiply the denominator by this. In order not to change the whole expression, you have to multiply the numerator by the same complex conjugate. Then no change in the expression. Okay. Then the next step is we just expand them. Okay. So now for expansion, as what I've done earlier for question 2, you just expand them. Just expand. Okay. So when you expand them, okay, the numerator, you will have 12 plus 9j plus 8j plus 6j squared.
So there's something wrong with your screen again.
Oh dear.
Yeah.
I don't know why it keep on coming on regularly, I don't know what is happening. Why it comes on regularly? It never happened yesterday. Something. I just click the AI companion only, and this thing keeps coming on. Okay, back to bit blur, right? Again, it never happened yesterday. Okay, all right. All right, let's continue. And you expand the denominator, multiply these two terms together. So you get 16 plus 12j minus 12j minus 9j squared. And remember, j squared is equals to minus 1. Okay, the numerator j squared, same thing, equal to minus 1. Okay, so therefore, since this is equals to minus 1, okay, and also this is also equal to minus 1, then we have we can, and also you have plus 12j and minus 12j, so these two will cancel off. And this j squared is equals to minus 1. So we have got rid of all the j in the denominator already. Okay. So now you just do housekeeping, clean it up a little bit. Right. So you have, so it's 12 plus, so it's 12 minus 6. Because this is whole thing is 6 times minus 1. 12 minus 6 give you 6. 9j plus 8j, 17j. Okay. And the denominator, you have 16 plus 9. Because minus 9 times minus 1 is plus 9. So 16 plus 9, 25. Okay. So now you just do one final step. Just split this up to real part and imaginary part. 6 over 25 plus 17 over 25j. And that's your answer. Real part and imaginary part. So the trick is to get rid of the j in the denominator so they can end up with a real part and imaginary part very nicely by multiplying the denominator with its complex conjugate. Okay, that means with a plus instead of a minus. Okay, all right. Okay, there you are.
Sorry, Prof. Can I ask about the Z1 minus over Z2?
0
So
minus 2, where is
No,
it?
Z1 over Z2, this question.
Okay, Z1 minus Z2.
So for the multiplying my 4 plus 3j, is it all the same? Like for example, Z2 is now 4 minus I know 4 plus 7j. Then if I would the multiplication be 4 minus 7j, the opposite?
Yes. It's opposite. Change the sign
Okay.
only.
Okay,
Change the
thank you.
sign. Okay, whatever you have stays there. Just change the sign. Change the sign. Okay. All right. Okay. Good question.
Then
Yeah.
clarification for the minus the j squared equals to -1. Will there ever be a case where we encounter j cubed, like j to the power of 3 or j to the power of 4?
Well, it is possible. It is possible. If j to the power of 4 is simply j squared times j squared, so -1 times -1. You know?
So then would it become +1, +1 then?
Yeah.
Oh, okay.
Yeah.
Then if there's a j to the power of 3, would it be
If
negative
j
j
to a
instead?
power of
Not
3
j?
in the numerator, then it'd be more complicated. So you will have a j, if you have j to the power of 3 in the denominator, so j to the power of 3 is j squared times j. J squared times j. So j squared is -1. J squared minus. So we end up with a j. Still
Okay.
have a j in the denominator. Then you multiply that in the denominator with its complex conjugate. You get rid of the j in the denominator. Same procedure, same step. You just expand it further.
Okay.
Okay.
Thank you.
All right, good. Okay, let's back to the screen
Professor, can you share the paper again?
again.
Paper back.
Okay. All right.
I just want to clarify. Can you go to the third column? Is it 12 plus 6? Or it should be
Third
12?
column, third row. Which
Yeah,
row?
the below.
Below.
It's 12 plus 9j plus 8j plus 6, right?
Yeah.
So
Yeah. Oh, this is 6j squared. 6 times -1.
Oh, yeah, the negative one.
So it's -6. 12 minus 6.
Oh, yeah,
So
12
give you
minus
6.
Okay.
Okay.
Thank you.
All right. Okay. Back to the screen. Oops. Okay. Right. So that's the answer. All right. So I've done this slide already. Okay, let's what's the next slide? Okay, so we've finished this topic. That's only topic 1 only. Okay, all right. We'll take a 5-minute break. All right. 5-minute break, then we'll
Okay.
come back. Okay, all right. See you later. Complex number. Okay, the one part B, the one part B, back to the complex number. Okay, so the one about Z1 minus Z2. So it's Z2 minus Z1. Okay, Z2 minus Z1. Okay, what you can do is, okay, this is your Z2 and there's your Z1. So the best way is just you can remove all the brackets. Okay, you put all the, or you can just put 8 minus 2j minus 13 minus 5j. Remove all the brackets and just add them up. 8 minus 13 minus 5 minus 2j minus 5j minus 7j. Answer. Okay, that'll be the easiest. All right, let's clarify all doubts. Okay, for 1B, that'll be the easiest. Okay, all right.
So for the last question, right, is it okay if we just leave it in the fraction form?
The last question, I mean the Z1 over Z2, is it? Last
correct. Can
question,
we just leave
Z1
it
over
as
Z2. Yeah, it's 6 over
17?
25 plus 17 over 25j. Yeah. Leave it as it is, as what I given you.
As in, can we leave it as 6 plus 17j over 25?
Normally we will put it as a real part and imaginary part. Real part rather than this. Not this. We want to clarify, to state very clearly that it has got a real part, which is 6 over 25, and the imaginary part, which is 17 over 25. So real plus imaginary. This is the final form. Okay, don't leave it in this form. Leave it like that. Real and imaginary. Not in this
Got
form.
it.
Okay.
Thank
All
you.
right. Okay.
Teacher,
Yeah.
can I ask that question, the most recent one?
Yeah. Most recent.
Yeah.
Most recent. This one.
No, after this.
After this. After the complex conjugate is no more already. Is there some more after this?
Wait,
After
just
this?
now you showed another paper, right?
Oh, it was before this one.
Okay.
Okay.
Yeah, is it better to leave the answer as like minus bracket 5 plus 7j?
No. Because for a complex number, you must have a real part and a imaginary part. Separate them. Okay, you don't put a bracket. Don't put minus 5 plus what? 7j.
Yeah.
I mean like that. No.
Okay.
Okay. Put it
Okay.
have a real part and an imaginary part.
Okay. Thank you.
Right, good. Okay, so next topic. Next topic, go to back to the screen. Okay, just now I show the QR code. For those who just joined, please, I hope you have scanned it and take your attendance for this morning session. So every session, you are required to take attendance. The same QR code, but it's recorded on as a different day, different session. Okay. Okay, this is okay, trigonometric. Okay, trigonometric and inverse trigonometric function. Okay, we know what is trigonometry. It involves sine, cosine, tangent, secant, cosecant, and so on and so forth. All right. So we're going to see how we're going to evaluate. First, must understand what these functions are, how the graphs look like, for the sine, cosine, tangent, secant, cosecant, and then how to evaluate them. And trigonometric function involves sine, cosine. So it will involve a waveform, sine waveform, cosine waveform, and so on and so forth. So there are many different kinds of signals. So these signals appear in a form of waveform when we talk about trigonometric functions. So these signals, for example, radio waves. See, radio waves, right? Microphone waves, and many. So not just electronic signal, but also mechanical. For example, you have a spring mass system. So this is a spring. Okay, this is a spring, this is a mass. It's called a mass. Spring mass system. Now, as it is now, the mass is resting at its equilibrium position. It's resting. Equilibrium position. Okay. Now, if you hold the mass and just pull it down a bit, and then you let go. Because when you pull it down, you stretch the spring. Okay, when you let go, the mass will start to oscillate up and down. Okay, here, up to there and there. All right, they will start to oscillate between its maximum height and the minimum height. Maximum position and minimum position. Okay, max and min. Okay, and the vibration of this mass is actually can be converted to a waveform, either sine wave or a cosine wave. Sine wave or cosine wave. Okay. Right. So in other words, sine, cosine wave, they actually called periodic waveform. Okay, periodic. That means it's a function of time and it repeats itself. The same waveform repeats itself over and over again. Okay, so a function like this, f x plus t. So you know it is a waveform of period t. Period t. Okay, right. Okay, I got a here a little video to show you a little bit more. on waveform. Okay, I hope it's working. I'm not sure it's working. If you can't hear anything or see anything, let me know, because Ishan video got problem. Ishan, when I show video, it has a bit of problem. Okay, it's playing now. Can you hear or see anything? Let me know.
Cannot.
I don't see any videos.
Can you see or hear anything?
No
No.
video.
No, don't see it,
cannot
don't
hear
hear.
anything.
Oh dear. Let me see. More. Share computer sound. Again, give me a moment. Okay, if I play again.
Can be confusing. So, first of all, at some point in my
Can hear, cannot see.
three mechanics.
Can hear but cannot see. Okay.
No video.
No video, but can hear the sound, right?
Yeah.
We
can
see
hear
the
it.
slides.
Yeah, we see the slides.
Oh, can see the slide. You can see the slide. You can see the. You can actually hear
Can
the
see
sound,
the
right?
slide, but no video. Can hear
No.
the sound.
Oh,
Yes.
okay.
Well,
Okay. Let me see. I have to give me a moment. Let me. Give me a moment. No. Video sharing.
Mechanics class, I always have a slide like this.
Can you hear?
When we're just getting ready to
Can you
do
see?
No.
rotational
Can
Can
On
hear
the
the
hear,
sound,
but
but no
cannot see
videos.
anything.
Still
It's just blanked
okay.
out.
remind the troops.
So I think you need to share your whole screen, not the app. I think you're sharing just the app.
I think I have to angular frequency. Okay, let me just angular frequency, angular velocity. Give me a moment. Okay, let me just try again. Okay, let me try again to share. Okay, can you see and hear?
Mass and momentum, force.
Okay, what I do is I will just move it to the relevant portion because some of these are beyond the bridging course. Okay, let me just slide to, let me see, to show the concept.
And so there's a little fact that the angle that the pendulum
Don't worry
makes,
about this. Don't worry about
frequency in
this. Give me a moment. Okay, somewhere.
Let's move ahead.
Here.
I have a little demo to show. Okay, so here I have a mass on a spring, and I'm going to be graphing displacement as a function of time. And just for reference, I've put here the equations that we use to describe these guys. And you can see that as the mass wiggles up and down, and we graph displacement versus time, indeed it does trace out something like a sine function. And the velocity, of course, goes like the derivative of that, and the acceleration goes like the derivative of that. So that gives you a sense of how it's going to go. I want to show you the phase at the same time. So let me add a graph that also displays the phase. Let's look at that. Okay, so same situation, except now we have the displacement as a function of the phase. So I'll go ahead and start it going, and everything looks about the same, except that now you see that I've got the phase here, and it's pretty well matched up to the other picture. It's just that now, by the time the thing gets about to its peak here, that should be a phase of about pi over 2, and by the time it gets 1/2 of a cycle, we've got a phase of about pi. There you go, 3/4 pi, and then 1 full cycle, of course, is going to be right around 2 pi. So there you can see that that's 2 pi. So the point is, instead of graphing displacement versus time, here I have a displacement versus phase, and 1 full cycle corresponds to a phase of about 2 pi. Now what do I mean by phase? Phase is just omega times t. It's the thing that goes into the sine function. It's called the phase, and it's sort of like an angle. But I want to basically support the idea that it's an angle, so that's the next demo. Okay, so here I have a similar setup, the box going up and down. Here I have a sphere that's going to spin around in a circle, You'll see that in a moment. And then I have this white stuff here. This is supposed to be some kind of like a chart paper. The chart paper is moving to the right, and it's just going to track the position of the block as it goes up and down. So let's see how that works. There we go. So the chart paper is moving to the right, and you can see that this is tracing out something like a sine function. I'd like to draw your attention to this thing going around. Notice that this is uniform circular motion, this red sphere, and the y-coordinate of the sphere is equal to the y-coordinate of the box at every point in time. And the notion is that simple harmonic motion is just like uniform circular motion, except it's projected onto one direction. So if you take the y component of this guy, it's always equal to the y component of the box, so the box going up and down behaves just like the y component of an object moving in a circle. That's the idea. Now, what happens to the angle that this object makes with the horizontal direction as a function of time? The answer is it just grows uniformly with time. And so we have the angular velocity of this object moving around happens to be equal to the angular frequency of this simple harmonic motion. And that's the way in which angular frequency and angular velocity sort of come to have the same letter. The angle here is called the phase. It's the phase of this simple harmonic motion. If we make a graph, let me go ahead and graph the phase here so you can see what it looks like. And I'll put that in the same chart. Let's run this thing again. And here we have a graph of the phase, and we'll start the thing going. See, there we go. And the phase, you can see, is just increasing linearly with time. And one way to think about omega is to say that it is the rate at which the phase angle is increasing. In other words, it's d theta dt still, but it's the d theta dt of the analogous circular motion. It's the rate of change of the phase, not
okay,
in
will
the physical system.
I will stop the video here, right? And back to the screen. Back to screen. Okay, can I go back to the screen? Okay, give me a moment. Okay, all right, back to the screen now. So basically, the video is to show you all how come for a mechanical system like this, okay, a spring mass system, we can have equations describing this motion, this vertical motion, yet it has got angular velocity, omega. Angular velocity, omega. People will wonder, this is just a vertical vibration, motion of the mass. If it's vertical motion, moving up with vertical velocity and acceleration. But how is there a omega, which is the angular velocity? How does it come about? And that video explains to you why you can actually explain with equations a vertical vibrating motion using circular motion to describe the vertical oscillatory motion. Okay, so right. So I hope that is clear. So this spring mass system, when you here on the left here, once you let go, because of the weight of the mass, okay, it will come down to here. Here, then it remains still. This is the equilibrium position, as what I drawn for you earlier. Now, if you were to pull this mass slightly below the equilibrium position, and then you let go, then the mass will start to oscillate. You start to oscillate, okay, between this and this, and this. It will start to oscillate. Okay, up and down about this equilibrium position. So this is the equilibrium position. In other words, it vibrates or oscillates. And if there's no air resistance, assuming there's no air resistance, then you continue to oscillate forever. But in reality, within our atmosphere, there is air resistance. So in reality, the oscillation will die off. Slowly, smaller and smaller Y values, smaller and smaller oscillation, and eventually you will come back to rest at the equilibrium position. Okay, right. So now we know that the oscillation can be plotted in this form, okay, in this form as a waveform. So now I'm going to refresh your memory on waveform principles and concepts. So the omega, this oscillatory motion, can be represented by omega. Means like in the video, you have the red sphere going round, the red sphere going out. Okay, as the red box oscillates, the red sphere will accompany the red box, and the red sphere will go around with an angular velocity omega. So angular velocity omega is equals to 2 pi frequency. Okay, so frequency F is in hertz or hertz. All right. Omega is the angular velocity. Okay, so there's one formula. Omega is 2 pi F. And the formula for frequency is 1 over t, related to the t. T is the period. T is the period. So now, if you look at this waveform here, okay, can you fill in the value in the white boxes? Looking at this waveform, what is the amplitude of this waveform? What do you think is the amplitude of this waveform?
150.
150. Very good. What's the period of this waveform?
4.
4 seconds. Okay, so for those who are not very sure, amplitude of this waveform is from the x-axis to the peak. Okay, x-axis to the peak. That is the amplitude. Okay, 150 units. Then the period is for one complete cycle. So if you see this waveform, it starts at 0. Okay, then it goes up, reaches the peak. Then it goes down. Okay, as time passes by, then it goes up. There's one complete cycle. Then from here, it starts to go up again. Just like here, it goes up. So it reaches here, it completes one cycle. Then it restarts again. It goes. So one cycle. The time for one cycle is called the period. So from there to here is a period T. So amplitude A. So period is 4 seconds. Okay. The frequency, what's the frequency?
1 over T.
Frequency is 1 over T. So it's 1 over 4. So it's 0.25 hertz. Okay. All right. From the earlier slide, the formula for frequency is 1 over T. T is 4. So 1 over 4 is a quarter hertz. Okay. Okay, that's very good. So if this is the mass or the object that's oscillating, then this is its equilibrium position. This is the equilibrium, EQM position. So it oscillates about the equilibrium position. Okay. So there are different types of waveform now. For vibration, normally it's sine or cosine. But for other signals, it could be different type of waveform. It can be a rectangular type of waveform. So some waveform, it could be, for example, can be like this. Okay, can be like this. About a equilibrium position. This line is centralized. Okay, you can have this kind of waveform. You can also have other types of waveform. Okay, that can go like that, come down, go like that, come down. So different types of waveform. But commonly it's sinusoidal. What you see here on this diagram, sinusoidal, like a sine wave. Sine wave and cosine wave are similar, except that one has a different phase angle compared to the other. So just now in the video, you also heard about phase. Phase. Okay. The commentator mentioned phase. So what you see here are two waveform. So you can recognize that the red one is your cosine waveform, because when theta is equal to 0, theta is equal to omega t, yeah? Here as the video mentioned in there. So cos omega t, when omega t is 0, which is here, okay, cosine 0 is equal to 1. So this red waveform is a cosine waveform. And the blue waveform is a sine, because when sine equals 0, when omega t equals 0, sine omega t is 0. All right, so blue is a sine waveform. Okay, so theta is equals to omega t, and theta is presented here not in degree form, but in radian form, radian. So pi over 2 is equivalent to 90 degree. Pi equivalent to 180 degree. And then 3 pi over 2 is 270 degree, and 2 pi is 360. Okay, so now, so between these two waveforms, we see that we can say that the cosine waveform leads the sine waveform. By how much? By pi over 2, which is 90 degree. Okay, again, the cosine waveform is leading, like leader, leading somebody, leading the sine waveform by pi over 2. In other words, the cosine waveform reaches 1 earlier than the sine waveform. Sine waveform reaches 1 later than the cosine waveform. By how much? By an angle pi over 2, by 90 degrees. So we see the cosine waveform leads the sine waveform by 90 degrees. So now there's a...
This pi is in radians, right?
Yeah, pi over 2 is in radians. Okay. And so this waveform, for example, the sine waveform can be represented by this expression here, you see. Y is equals to A. A is the amplitude of the waveform, and sine bracket omega t plus phi. Omega t is your theta, and phi is the phase shift. Yeah, phi is the phase shift, or the angle, phase shift angle. Now you will come across this in again in control, in robotics module most of the time, but it can also happen in other. It can also occur in other modules as well. But you definitely see in your mathematics module. Okay, so here again, let me just okay. All right, so again, this will explain it clearly. Okay, phase shift. So again, here we have 3 different waveform. You have the blue one or purple one is waveform C. It's a green waveform D, and the red waveform E. So they are different, and they are sinusoidal. Okay, they're different amplitudes. Okay, and okay, on this here is plotted as degree lah. But you see, degree can be converted to radian easily. Okay, so usually people put in radian form, but on this graph, they put in degree, but it's okay. You can easily convert degree to radians. So we therefore say that C, waveform C, okay, because it reaches the peak earlier than the green and the red. So C is leading D, and D is leading E. Okay, and in terms of lagging, we say that D is lagging behind C. Okay, and then E waveform is lagging behind both C and D. So lead and lag. Lag is the opposite of lead. So in control and in mathematics, you see words like phase shift. This waveform is leading. That waveform is lagging. So now you should understand what it means lah. Okay, right. Okay, so now about this omega. Why you have omega? Again, the video they explain it did explain it very well lah. And how come we have omega when a mass is oscillating in the vertical direction? You see, you have this omega coming in. So on the video, the red sphere is actually represented by whatever is on the circle. And the red box on the video is actually your mass, the red box, actually your mass. So box in your video, that's the red box, okay? And this is a sphere on the video that's rotating. So if you look at this, right from the very beginning, okay, this is the first, oops, very sensitive. Let me just give me a moment. Okay. So now, so this is your diagram 1, diagram 2, because they are all moving. 3, 4, 5. Okay. Now, so at the start, look at diagram 1, or let's say and then in this case you have 2. You have 2. 2. I'm explaining there are actually 2 bodies, 2 bodies that produce this curve, red and the blue. So at the beginning, okay, your red dot is here. Sorry, blue dot is here, the red dot is there. Okay. So when the mass box starts to oscillate, okay, this dot here on the circle will follow. Okay. So from 1, the box is here. Okay. And if there's another dot is there, let's say it belongs to a different mass. So you have the blue waveform and the red waveform. So when the dot starts to move, okay, blue dot starts to move to here, its corresponding box is here. When it starts to move, both start to move at the same time. Same time. And the red dot move, its corresponding box is there. You see? All right. So it's moving with a velocity omega. So in the third diagram, the blue dot moves to here. The red dot will move to here already. Fourth diagram, the blue dot move, so it moved to here. And the red dot correspondingly move to here. Okay. In the fifth diagram, red dot move to here already, as shown here, and the blue dot move to here. Okay. So, and the shadow, because of this moving, their corresponding boxes will also follow. So they follow. Okay. So we are therefore able to describe the vertical motion of box or boxes with by having expressions involving their corresponding spheres moving in the circle with velocity omega. Okay. So here you see that at the beginning, the red dot, which corresponds to the red waveform, is already leading at the start. It's already 90 degrees ahead of the blue waveform there. Okay. So when you start, both will start to move around in uniform velocity omega. And in other words, it will go like that. And the blue waveform will follow, will go like that, you see. So we therefore say that the red dot leads the blue dot by pi/2 or 90 degrees. Or in other words, the waveform, the red waveform leads the blue waveform by 90 degrees. Okay. Now, if now you just assume that there's only one waveform, okay? Assume that there's only one. Don't worry about the circle anymore. Look at the waveform. If there's only one waveform, okay, red color waveform. And then later on, through some process, the red waveform has moved, and is shown by the blue color, okay, has moved. So we say that the red waveform has shifted to the right, Okay, shifted to the right. So there's a phase shift to the right. We call it a phase shift. That's how we use the word phase shift. And how much is the shift? By pi/2, 90 degrees. Okay. So I'm trying to explain phase shift and trying to explain why there's an omega for an object that is oscillating in vertical motion. Okay. Now, next is the arc length. Length of an arc length. So arc length is when you is on a circle. That's the arc length. Okay, that's the arc length. GTH. That's called the arc length. All right. Now, people would always wonder how come 1 radian is, 1 radian, how much is 1 radian? 1 radian is equivalent to 57.3 degree. 1 radian. How do we get that? So you look at this diagram here, okay, and look at this blue spot, blue dot. Okay, the blue spot starts from the x-axis. And so it moves from there to there. Okay. Now, with a radius that is 1, radius 1 unit. Okay. When this arc length is equal to the same length as the radius. Okay. When the arc length, let's say S, and this is R. Okay. When this dot has moved and moved and moved, as it moves, the angle theta changes. So when it moves to here, when the arc length S becomes equal to R, and you stop it there, you measure this angle. This angle will be 57.3. Okay, the formula for arc length is S is equal to R times theta. Remember this formula? Arc length is equals radius times theta. Okay, so therefore, theta is equals to arc length over radius. So when arc length is equal to radius, so when arc length is equals to radius, then you measure theta will be equal to 57.3 degree. Okay, so that's a definition for the radian. Means theta is equal to you measure you find it's 57.3 degree, and because you see theta is close to 1 radian. Okay, when this happens, when S goes to theta, then theta is close to 1 radian, and you physically measure theta. Use a protractor or whatever to measure theta. You find that theta is 57 degree. So 1 radian is equivalent to 57.3 degree. Okay, right. So now we know why 1 radian is 57.3 degree. Right. So so the conversion of degree to radian are shown here, equivalent of degree in radian form. For example, 30 degrees is pi over 6, 90 is pi over 2, 180 is pi radian, 360 is 2 pi radian. Okay, so the conversion is always easily done. Okay, okay, so much about radian and so on and so forth. So now let's look at the waveform. So when you see something like this, you know it's a sinusoidal waveform. It's either a sine waveform or a cosine waveform. Okay, and you can see here the period is 2 pi. Okay, complete 1 cycle. Time to complete 1 cycle is 2 pi. Okay, so for this waveform, okay, as you can see here, the sinusoidal, and first thing we need to know that sine x plus pi over 2 is equal to cosine x. Okay, this is one of the first expression we need to know. Why is this so? Why is this so? Because sine x plus pi over 2. Okay. When you expand it using identities, it's sine x cosine pi over 2 plus cosine x times sine pi over 2. We expand it using identity. Okay. So sine of 90 degrees is equal to 1. Cosine of 90 degrees is 0. So you end up with cosine x. Okay. So you see the phase shift between sine and cosine waveform is pi over 2, 90 degree. Okay. All right. Let's solve some problems involving sine and cosine. Okay, this example here, find all solutions of the equation A, 2 sine x minus 1 equals 0, and B, cos square x minus 3 cos x plus 2 equal to 0. Okay, I give you some time for you to solve this. Okay, you go ahead and try to solve. In other words, find the final expression involving x. The final expression involving x. Okay, you can start now. Give you some time to solve these two problems. Okay, please go ahead.
Wait, Professor, should we do this in degree or radian?
These are all in radians.
Okay.
Yeah. Okay. Done already? Okay, done, All right. Okay. Okay, now you can check your answer. I'll go through and see whether you got it correct or not. Okay, I need to use the visualizer, so I need to switch to visualizer. Okay, all right. That's how we start. Okay, A, let's do A. Right, can see? All right. So we have this expression 2 sine x minus 1 equal to 0. And we are to solve for x. Okay, solve for x. So i.e., that is, i.e., we have therefore sine x is equal to half. Okay, bring the 1 over there, then bring the 2 below the 1. Okay, sine x is equals to half. So sine x equals to half, and what should x be? You find that x actually will be 30 degrees. Okay, x is like theta. It's like theta. Okay, x will be 30 degrees. All right, use your calculator. X equals arcsine half will give you 30 degree. Now, do you all get 30 degree, which of course in radian form would be x is equal to pi over 6. Do you get pi over 6? Let me just check. Yes. Only pi over 6. Do you get something else plus something else? Pi over 6 plus something else besides pi over 6? 5 pi over. Okay. Pi x over 6, or someone got x is equal to 5 pi over 6. Any more besides pi over 6 or x equals 5 pi over 6? Or any more? Any more? No more, is it? No, no more. Okay. Very interestingly, Very interesting. Let's draw the quadrants again, the quadrants. Okay. So we have these the quadrants. All right. So pi over 6 is actually 30 degrees. So this is sine. So 30 degrees is there. Also, x can also be 5 pi over 6 radian. 5 pi over 6 is how many degree? 150 degree. Okay. So 30 degrees from the positive x-axis up. Okay. Up. Then when you have 5 pi over 6, which is 150 degree. So the 150 degree is measured from here, here to there, 150 degrees. Okay, so these are the two possible answers of x. Is that correct? X is either equivalent to 30 degrees or equivalent to 150 degrees, because it says that x is pi over 6 or x is 5 pi over 6. Now, then don't forget, okay, you can use your calculator. You key in sine 30 degrees, it will give you half. You key in, find out sine of 150 degree, 150 degree. Okay, sine of 150 degree, it give you half also. Okay, now you try to key in sine of 390 degrees. Sine of 390 degrees. What do you give you? It give you half also. So there are more degrees, you know, not just 30 degrees and 150 degrees, but also 390 degrees.
So can we leave it in terms of n to show the expression?
Okay, we'll come to it. Then you key in sine of 510 degrees. Okay, sine of 510 degrees, also half. Wow, so you see that there are not just two angles or three angles. There are actually many. So in other words, so one answer is 30, next one is 150, all right? Then next one, you go around, reaches 390 degrees is also an answer. Okay, and then it also go around for this one. When you go around to, you go past 360 and past this and comes to here. It also give you another answer for x. Then you can just continue and continue, just go on and go on, go on and on and on. So not just two answers or three answers, but many answers, because it says find all solutions. Find all solutions. So all solutions are all possible solutions. This is for the, each time you go around, you go around, you go around. So plus 2n pi. Pi means you go one round now. You just go from here, you go one round, 360 degree. Then you come to the next one. Then you go on, another 360 degrees, another 2 pi, another 2 pi, another 2 pi. You come to the same, okay? Like 30 degree, right? Pi over 6. Now you go 2 pi round, means one round, you get what? 390. So it's 2 pi n. You get your 290. And then another 2 pi n equal to 2, you get come to here, you get another answer, and so on and so forth. Where n, what is n? N start from 0, the next one at 1, 2, 3, and then continue. You just go round and round and round and round. There's no end to it. And this will capture this, and this will capture all the possible answers to this problem. All the possible answers involving x. Okay, so not just two answers or three answers, but many. And can just go around to very large value. So if you, in a quiz, in an exam, you just give like that, you won't get full marks. You have to present this and this to get full mark. That means you know what you are doing. All possible answers. This take care of the 30 degree. Then you go around to, they come to the same 30 degree area, but it's already gone around 2 pi, you know. Then you go around again, another 2 pi, and then go around another 2 pi. So n just continue to increase from 0 to 1 to 2, you go around one more round to 3, one more round to 4, one more round to 5 to 6. Let's go on. And same for the 150 line. All possible answers.
So when I give my answer, I need to write where n equals to 0.
Yes. N starts from 0. Because when n is equal to 0, there, it's pi over 6, 30 degree. Then when n is equals to 1, that means it go around 2 pi already. It's pi over 6 plus 2 pi, n equal to 1. That means it's your next one is your 390 degree.
Do we need to express in a set?
In a what?
In a set.
Oh yeah, of course. You need to present these two. This for the 30 degrees. This is for the 150
But
degrees.
n equals to positive integers.
Oh yes. Yeah. I always people know what your n is, you see. What is n? If you ask you what is n? N is it 5 or 8 or 20? People will know. You have to have this. Right?
Okay. Thank you.
Right? Okay, so this is for A. All right. So I think most of you did not get these two. You only get this or this, right? So you not get full marks for that. Okay, now we go to B. B. Okay, B is cosine square x minus 3 cos x plus 2 equals 0. Find all possible solutions of x. Okay, so you rearrange. You rearrange. Or in fact, you don't rearrange, also can. You can factorize this. You can try factorize it using the bow tie method. Okay, I just cut it short using bow tie method. So this all right. So like that. Okay, here is cos square x. So we can put cos x and cos x. Okay, and here is plus 2. So plus 2 can be 2, 1, and you have to look at, see which one should be minus, which one is plus. But it's plus 2, you see, so it's minus 2 times minus 1 give you plus 2. We'll look at the bow tie method later on in the course to refresh your memory. So this can be factorized into cos x minus 1 times cos x minus 2, i.e. cos x minus 1 cos x minus 2 equal to 0. So here, what does it mean? It means, i.e., cos x minus 1 equals 0, or cos x minus 2, n, if you like, equals 0. i.e., cos x equals to 1, or n, cos x equals to 2. Okay, you break this up. Okay, you look at these two equations. You look at this one first. Can cos x be ever equal to 2 or not? Maximum value of cos x is plus 1 or minus 1. It can never be equal to 2. So this is rejected, inadmissible, rejected. You can have cos x equal to 1. When cosine x equals to 1, i.e. x will be equal to 0. Cos of 0 equal to 1. Okay? And as before, what you've done here, cos of 360 degrees also equal to 1. Use your calculator, you can see. So 360 degree in terms of radian is 2 pi. Okay? Then in the same way, you have to go round again another 2 pi. Okay, another 2 pi to reach 720 degree. Use a calculator. Cos of 720 degrees also equal to 1. And 720 degree is 4 pi. Then go on again, same way. Okay, go another 2 pi. Look at cosine of 1080 degree. 1080 degree cosine. You will get 0. You get 1 cosine that equal to 1. Okay, so 1080 degree is 6 pi, and so on and so forth and so on and so forth. Okay, and so on and so forth. So all solution, you must capture all solution. So just like summation sign, but of course here there's no summation. We use n, okay? So it's therefore 2n pi. Again, where n, you must put this, where n is equals to 0, 1, 2, and go on forever. Okay? Because when n is 0, x equals to...
The video is down.
Prof, your screen share.
Yeah.
Prof.
Wait. My screen share. I don't know why it happens.
Prof.
Wait. Okay.
Okay, it's back on now.
Okay, I don't know. It happens at regular interval. Okay. All right. So yes, you represent this x, these possible values of x using 2n pi, where n goes from 0 to 1 to 2 to forever. So when n is 0, x is 0. When n is 1, x is 2 pi. When n is 2, x is 4 pi, and so on and so forth. So that would be your answer, and you must put this also. So you get full marks, okay? So remember, when something like this, x has many, many possible answers which are correct, okay? All right, let's, okay, all right, good. So far, so good.
Sir.
Yeah.
If just now you're talking about the butterfly, right? But then I got another way. Like, can we use the quadratic equation?
Of course, you can. Remember, I always say many roads lead to Rome. Many roads lead to Rome. You'll get the same answer. Possible,
Okay,
yes,
thank
of
you, sir.
course. All right, let's back to the waveform thing. Back to the screen. Where is it now? Okay. All right, so we've done that. Okay, next. All right, so there are many other types of waveform, not just sine, cosine, but also tangent. Okay, tangent x or tangent theta is sine x or sine theta over cosine x or cosine theta. Okay, tangent is sine over cosine. So this is a tangent waveform. The blue color. Is a tangent waveform. Okay. Now the vertical line is called asymptote. Asymptote is a line that can never be touched by a tangent curve. So the tangent curve, as it goes upwards, will gradually, very slowly approach the asymptote, but it will never touch. It will never touch the asymptote. It will forever, all the way to infinity, go moving parallel to the asymptote, but never cross the asymptote. Okay? Same in the negative direction also, negative y direction. You will continue to approach the asymptote, but you will never touch the asymptote. That's what's meant by asymptote. So this you can see this is a typical tangent waveform. And then a cotangent waveform. Cotangent is cosine over sine. So a cotangent waveform, same, also have asymptote. And the cotangent waveform will never cut through the asymptote. It will approach the asymptote by still approaching. At infinity, still approaching, but never touch the asymptote. Okay. Then you have this is your secant. Okay, with a cotangent. Okay. This one is the secant. Wait, go back. So this is secant x, which is 1 over cosine x waveform. Okay, this is a plot of secant x, just for you to appreciate the waveform. Okay, so it has asymptotes also. Then cosecant is 1 over sine x. Okay, this is a waveform if you plot it. Okay, all right. So we have more or less briefly looked at waveform. Next is to refresh your memory on identities. Okay, identity. That means identity means this expression will always be true, regardless of the values of alpha. Always be true. Regardless of the range of alpha, the range of beta. Always true.
Teacher, can I just ask, right?
Yep.
During exam, do we
Yeah,
have
given.
this formula sheet?
Yeah. Depends on your module lecturer. lah. Some exams are closed book. Some exams are closed book. You can bring in a cheat sheet. Okay. Some are closed book, but the relevant formula needed to solve that problem is given next to that question. So it depends on your lecturer. I cannot speak on behalf of all your other professors because they have their own way of doing things. So I cannot speak on their behalf. Okay. But this course is to refresh your memory, to let you know that there are identities. And there are many, many, many identities. I'm just trying to show you the initial, just to open up your mind again, refresh your memory. So identities, why they are called identities and not called equations? You see, identity means this expression, these equations are always true, but they are specifically called identities because they are always true. Now, equations are not always true. It's surprising to hear, our bridging course professor said equations are not always true. No, yeah, which is correct. Because some equations are only applicable for certain range only. When the values of, let's say, x falls within a certain range, then these equations are applicable. Outside certain range, these same equations will not be applicable, depending on the range of the x in the equation. Because some equations, regardless of x value, is always true, and that's all right. But for identities, you can always be sure that all these expressions are always true, regardless of the range of alpha and beta. That's why they are called identities. So now we know the difference between identities and equations. Okay, all right. So sine alpha plus beta is sine alpha cos beta plus sine beta cos alpha, and cosine alpha plus beta is cos alpha cos beta minus sine alpha sine beta. Sine squared alpha is half bracket 1 minus cosine 2 alpha, and cos squared alpha is half bracket 1 plus cosine 2 alpha. Then plus some more, there are many more. All is just to refresh. Okay, you go into internet and you key in identities. A lot of identities will come out. For me, you see, for my quiz and my exam, I would usually allow cheat sheet. Okay, cheat sheet. And sometimes I also put the relevant formula for that particular problem next to that problem. Okay, because I don't expect students to remember a lot of things. Even I also cannot remember long list of identities, how to remember them. But some other professors, they are different. It's a closed book exam, closed book test, and no cheat sheet at all. It means they expect students to remember. So different professors, there are different ways of coming up with exam papers and test paper. So I cannot speak on their behalf. Okay. So you can always test. Example, how do you test whether it's true or not? How do you test? You put in values. Example, sine, let's say alpha is 20 degrees and beta is 30 degrees. Okay, all right. And then is it equal to sine 30 degrees cos 30 degrees plus sine sine 20, 20, oops.
Prof, your screen.
Prof.
Okay. Why this screen appear in regularly? I don't understand. Give me a moment. Back again. This is 20 degree. Sine 20 degree cos 30 and sine 30 degrees cos 20. You see left hand side equal right hand side or not? Eventually they should equal. You find that this will be sine of 50 degree. Sine 50 degree, use calculator 0.50 I got 0.766044, 044, okay? Your right-hand side, you use calculator, you come to the same thing, 0.766044. So that's okay lah. So this identity is true, ma. That's how you test identity. You put in some values in there and you apply, put it into your identities, and you can check that it's all true. Okay, left-hand side equal to right-hand side. Okay, yeah. Right.
Prof,
Yeah.
can I take a look at the second, the previous graph that you showed?
Previous graph. This
Yes.
one.
Second.
Second.
Second. Okay. Thank you so much.
Okay. All right. Let's go on. All right. So we have finished this topic 2. Topic 2. Any questions? Any questions? I look at your chat box. Any question?
So can you go back to the previous slide?
Previous slide. Oh, this one. This one. Okay. Yeah.
I just need to refer what you writing. The
okay.
thing blocking.
Oh, blocking. Okay. Let me. Okay. All right. All right.
Hi, Prof. I wanted to ask that for. Wait, let me go back to that page. For slide 13, right? Where n is equals to 0, 1, 2, 3, why wouldn't n like go backwards? So like -1, -2, -3. Because
13.
there's no range for cos x.
Let me go back to 13. 12. This is 13. Oh, this one. Which is okay. This visualizer got to show the visualizer because it's on visualizer's paper. It's on paper. So this one. Is it? Are you referring to this one? Okay.
Yeah.
Your question is?
So why wouldn't n be equals to -1, -2, -3? So essentially n would be all real integers.
Yeah, because n has to be positive. If you go, because easier for us to understand if we move forward, if you say n is negative, then you would have minus, you see, -2 pi, -4 pi, -6. Then you're going the opposite direction, which is very weird. Because we're interested in all the answers of x. So we go from 30, then next x value is 150, and then next x value is 390, the next x value is there. So we're going, if you want to go the other way, if you put, you want to go the other way, it's very odd, but you can, but it's going to cause confusion, because when you talk about angle, you normally start from where? Your positive x-axis, you go this way. You seldom go this way, the other way around. You don't walk backwards. You always walk forward, right? When naturally you walk along the road, you walk forward. You don't walk backwards. You don't walk backward to walk forward. You see what I mean? You don't turn around and walk backward in order to walk forward. To the MRT station, you'll fall down.
Okay, I understand that for the ease of explanation, it would be 0, 1, 2, 3.
Yes.
But then in this case, the question didn't state that cos x has a range. So essentially negative.
No, all possible, all possible solutions.
I'm trying to say that
all possible solutions.
Yeah, so for all possible solutions, there should be a negative because there's no range, right?
Oh, x has a range all the way to infinity.
What about negative infinity?
Negative, I mean, okay, what you can do is you can on your own tonight, you can put n equals to minus, and you draw this curve. You draw this circle and see how it will just go the other way. It could go the other way.
Of your visualizer not showing.
Yeah, I don't know why it regularly, happens. Only for today. Yesterday was okay. Okay. All right.
Okay.
Yeah.
Okay.
So we always go forward to find all the possible values of x. You don't come to here after that then go backward. So if you go backward, you want to go backward, x is 0. Then you want to go backward. You will go. It has to come to here and here. You see. You come to here and here. So if that's the case, you will end up with it looks strange. To us, we're walking backwards. all possible solutions. You see, when you do this, you capture all possible solutions anyway. You capture all possible solutions. We're not going linear, no? We're not going x and minus. We're not going like what you normally think of graph, going positive infinity, minus infinity. We're looking at the angle. The angle. Angle go round. It does go to there and there. So we're converting this angle into radian. We're not going to like that, positive x, negative infinity. No. We're basically going round and towards many rounds, infinite number of rounds. And with each infinite rounds, we're converting the angle to radian, that's all. So if you like, the infinity is this way, you see? We're going this way. This is our rotational circular path towards infinity. Okay, we're not going like that and like that. Okay,
Prof.
Yep.
Can I ask why do you use the cosine x minus 1 and minus 2? Is it just for example?
Oh, yeah. I mean, from this problem, the problem says find all possible solutions of x for this. This problem is in a slide. Problem 1 in a slide, problem 2 in a slide. Solve for x. Basically, it's just solve for x. Okay, solve for x. So in this case, x not just like one value or two value. Yes, infinite number of values to get a full marks. Okay, so be careful when you solve equations involving sine and cosine. Don't just give one answer, 0 or 2 pi. It's a many infinite number of answers to get a full marks. Okay, all right. Okay, so it's 12 o'clock.
Forward, I can screen.
Oh, go forward. I think
sorry.
this is okay. All right. Okay, screenshot. Okay. Have you all done your attendance taking? Those who join in the middle of the class. Okay, I will show the QR code again. QR code. Give me a moment. Where's the QR code? The QR code. Okay, please scan, and then we can call it a day, We can call it a day. Okay, so but don't forget, see you in physics. 1:30 is a physics lesson. Okay, thank you very much. Thank you. See you in the afternoon, 1:30. Okay.
For the attendance, why it's showing the afternoon session? It's not showing the math session.
Now we're showing afternoon already, is it?
Yeah,